Yes, sir.
Yes, sir.
Okay. So let's start our class. So in our last class, we finished up to our three-phase diode rectifiers. Okay. So we have finished our uncontrolled portions. So diode rectifiers means we are talking all about, we had talked about uncontrolled rectifiers. So from this class, we'll be talking about our controlled rectifiers. Okay. Now, whenever we are talking about our controlled rectifiers, obviously we are talking about the diodes will be replaced by our thyristors or our silicon controlled rectifiers. That is our SCR. Okay, so let us see what is this control rectifiers first, and then we'll be trying to decipher all the individual control rectifiers one by one. Okay, so the first one is first we have to understand what is control rectifiers. The control rectifiers are nothing but line commutated AC to DC power converters. As you can see, it is written, it is a line commutated AC to DC power converters which are used to convert a fixed voltage, fixed frequency AC power supply into variable DC output voltage. Okay. So what we can understand that there would be an AC input voltage of a fixed frequency and a fixed voltage, and we'll be getting after passing through the line commutated converter, the output that we'll be getting is a DC output voltage which can be of variable DC output voltage. In other terms of also, we'll be later seeing that there are actually different types of line commutated converters where we are converting the AC input voltage into variable AC output voltage also, and we can also convert the AC input voltage into AC output voltage of different frequencies. Okay, we'll be seeing it in the next slide only. Just let us talk about the thing that we will be talking about in our class. Okay, okay. Shall I record the session? Yes, shall I record this? Okay. Let me start the recording. Okay, so the recording will be starting after a few seconds only. Okay, so as you can see, what we are talking about a phase control rectifier, phase control thyristor actually. So in the control rectifier circuits, we can obtain variable DC output voltage and variable DC output current by varying the trigger angle. So basically, we'll be controlling the gating. We'll be providing a gating signal to the phase control thyristor, and depending upon at what angle we are providing, we are triggering the thyristor would be operating, and the output we'll be getting a pulsating load current waveform. Means it would be a unidirectional and pulsating load current waveform which has a specific average value. So what we can understand is quite simple, is that the thyristors will be forward biased when during the positive half cycle of the input cycle, and will be turned on by applying a suitable gate trigger pulse. Okay, and will be turned on by applying a suitable gate triggering pulse at the thyristor gate leads. Okay, I hope that you have started learning about the SCRs in your other half of power electronics. Okay, so what will happen then when the thyristor is turned on? So the thyristor current and the load current will begin to flow when the thyristors are triggered, that is when they are turned on. We'll be seeing it later, say suppose at omega t equal to alpha. Okay, so the load current will be flowing when the thyristors will be conducting from alpha to beta. Okay, and beta, that is omega t equal to beta, is the time when the load current, or is the angle at which the load current will fall to zero. Okay, and when the load current falls to zero, the thyristor turns off due to AC line commutation. Okay, so obviously when that thyristor is conducting, one thing is we can understand that the output voltage across the load will always follow the input supply voltage through the conducting thyristor. Correct? Now, as I was saying that there are different types of line commutated converters. Let us look into some of them. So as you can see that what are the different types of line commutated converters? They are phase control rectifiers, which are AC to DC converters. Okay, we have AC voltage converters, okay, which convert the AC input voltage into variable AC output voltage at the same frequency. Please remember, at the same frequency. And we have cyclo converters, which gives us low output frequencies. And as you can see that all these power converters operate from AC power supply at a fixed RMS input supply voltage and a fixed input supply frequency. That is understandable. If the frequency varies, then obviously the output frequency will also be changing. Okay, but they use AC line commutation. What do you mean by that? What we can understand that the whenever the thyristor is going to zero, then the thyristor would be means whenever the thyristor current or the load current falls to zero, the thyristor will be turning itself off. Okay, so that is what is known as our basically AC line commutation. So they use AC line commutation for turning off the thyristors after they have been triggered on by the gating signals. So the application of these phase control rectifiers are huge actually. So DC motor control in steel mills, paper and textile mills. We use our electrochemical and electrometallurgical processes, AC fed traction systems, magnetic power supplies, reactor controls, portable hand tool drives, variable speed industrial drives. Very much important because many problems can be given from even on this control rectifiers through this portion. Again, when you're talking about machine specialization, you'll be often we will be talking about this variable speed industrial drives in details if you take machine specialization. Okay, then we have battery chargers, we have HVDC transmission system. We have talked about, we'll be talking about it. I think you'll talking about it in your power system planning and design classes. Okay, high voltage DC transmissions. Then we have the uninterruptible power supply, that is our UPS systems which we use nowadays. Okay, so what happened is that some years back this AC to DC conversion was achieved using this. How we were able to achieve this AC to DC power conversion? This was achieved using our motor generator sets. Okay, and we also use mercury arc rectifiers. But obviously, what we can understand that the modern AC to DC power converters are designed using high power, high current thyristors. Okay, so with the advent of the power electronics, we can use high power and high current thyristors. And so also presently, most of the AC to DC power converters are these thyristorized power converters. Okay, so these phase control rectifiers or the phase control converters are very simple and are less expensive and are widely used in these industrial applications as can be seen listed above. Okay, so these converters are classified as, actually they are known as our two converters. These converters are classified as two quadrant converters. That is, if the output voltage can be made either positive or negative for a given polarity of output load current. Okay, for a given polarity of output load current. So there are also single quadrant AC to DC converters where the output voltage will obviously be having only having one value, that is positive. So output voltage is only positive and cannot be made negative for a given polarity of output current. Obviously, for the single quadrant converters can also be designed to provide only negative output voltage also. Okay, only negative DC output voltage. And two quadrant converter operation can be achieved by using fully controlled bridge converter circuit. And for single quadrant operation, we will use a half controlled bridge converter. As we will be proceeding through this lecture on control rectifiers, we will be seeing that which one is used as a two quadrant converter and which converter circuit is used as a single quadrant operation. We'll be able to see it. Okay, so let us see now the control rectifiers. What are the various types of control rectifiers? As you can see, so just wait. Yes, it is changed, I suppose. Yes. So as you can see, these are the various types of control rectifiers. So the first control rectifiers can be divided in two parts: single phase, three phase. So again, we'll be as we have done for our uncontrolled rectifiers portion. So we'll be proceeding the same way that we again will be dividing this single phase into two types: half controlled, half wave control, and full wave control. Full wave again will be two types. One would be with bridge controlled and with the center tap transformer, and the full wave rectifier with bridge control rectifiers, that can be again divided into single phase semi converter. That is, one is a diode and another one is a thyristor we'll be using, and a single phase full wave converter. Okay. Again, similarly, we'll be using a three phase control rectifiers where we'll be dividing it into three phase half controlled and three phase full wave controlled. And this three phase full wave control will divide into three phase semi converter and three phase full converter. So let us start with the first one, that is single phase half wave phase control rectifier. Okay. So single phase half wave phase control rectifier. So as you can see, the very this particular signal is very easy to understand that what is happening. So obviously during the positive half cycle of the input supply, okay, during the positive half cycle of the input supply, as can be shown here, okay. So the transformer, what will happen that so as you can see, during the positive half cycle of the input supply, the transformer secondary is at a positive potential with respect to its lower end. Okay, is at a positive potential with respect to its lower end. Okay, and obviously when this is positive, so the thyristor anode is positive with respect to its cathode. Okay, so the thyristor anode is positive with respect to its cathode, and the thyristor would be in a forward bias state. Okay, and this so what is happening now? So this thyristor is triggered. So this thyristor T1 is triggered. Okay, triggered at a delay angle of omega t equal to alpha. Okay, so this thyristor is triggered at a delay angle of omega t equal to alpha, obviously by a suitable gate trigger pulse to the gate lead of the thyristor. This is the gating lead of the thyristor. So this thyristor will be triggered at omega t equal to alpha by applying a suitable gate trigger pulse to the gate lead of the thyristor. So after which, what will happen? After which this thyristor will start to behave as a closed switch. Okay, so it will behave something like this. It will start to behave like a closed switch. Okay, so what will happen now? So the input voltage when the thyristor is on, so the input voltage, this voltage will appear across the load when the thyristor will be conducting from omega t equal to alpha to pi radians. Okay, so the input supply voltage across the load, so the input supply voltage will appear across the load when the thyristor will be conducting from omega t equal to alpha to pi radians. So what will be the output? So for this condition, for omega t equal alpha to pi, the output V0 would be equal to Vs when this thyristor is conducting from omega t equal to alpha to pi radians. Okay, this thing is very clear. So with this in mind, we can easily draw this figure, as you can see. So this is the typical figure. So when the input supply voltage, as you can see here, so the input supply voltage is here. Okay, so during the positive half terminal, what is happening? The thyristor is in the forward bias state. So at omega t equal to alpha, what is happening? The thyristor is triggered. So as you can see, at omega t equal to alpha, the thyristor is triggered and the output voltage waveform will follow the input voltage waveform. So at omega t equal to pi, what is happening? As you can see that the current will obviously be again, that the output current will obviously be in phase with the output voltage. Why? Because if you have seen properly, this is a resistive load. Okay, so the output voltage the output voltage and the output load current will be in phase. Okay, and what we can see that the output load current waveform will be similar to the output load voltage during the conduction time from omega t equal to alpha to pi. Okay, so the load current will increase as the input supply voltage will increase. Okay, so load current will increase as the input supply voltage will increase, and the maximum load current will occur at what position? Obviously, we can understand that the maximum load current will occur at omega t equal to, what can we understand from the figure, that it will occur at omega t equal to pi by 2. Okay, omega t equal to pi by 2, the maximum load current will be occurring. So the maximum load current flows at omega t equal to pi by 2. Let me write it equal to pi by 2. Okay, so at this condition also the input supply voltage is maximum. So what we can write then? So we can write I0 max is equal to nothing but Im equal to Vm by the load resistance RL, and the source current Is can be written as how much? It can be IT1 equal to I0 equal to V0 by R. This is nothing but equal to Vm sine omega t by R for Which portion it would be? For alpha, less than equal to omega t less than equal to pi. I hope it is clear. Okay, this will be the source current. So when the load current will be flowing, then only the source current will also be flowing. So IS will be equal to IT1. That is the IT1 is the current through the thyristor, equal to the load current, that is I0, which is equal to V0 by R, which is equal to Vm sin omega t by R. And obviously I max, that is I0 max, would be equal to Vm by RL, because the load current increases as the input supply voltage increases, and the maximum load current flows at omega t equal to pi by 2, since the input supply voltage is also at its maximum. Okay. Now, what is happening in the negative half cycle? So, as you can see in the negative half cycle of the input supply, when the supply voltage reverses and becomes negative, that from omega t equal to pi to 2 pi by to 2 pi radians, what is happening? The anode of this thyristor. Okay. So, the negative half supply. So, during the negative half cycle, the terminals would be reversed. Correct. So, the anode of the thyristor is at a negative potential with respect to its cathode, and obviously that, so because of that, the thyristor is reverse biased, and hence it remains cut off. Okay, and hence it remains cut off. As you can see that there is no thyristor current or the load current flowing. Okay, so it will behave as an, under the reverse bias condition, the thyristor will behave as a what? It will behave as an open switch, and therefore there will be no output current and voltage during this period, and both the load voltage and the load current would be zero, as can be seen from here. Okay, and obviously what will happen? So the maximum or the peak inverse or the peak reverse voltage that appears across the diode, or means across the thyristor, sorry. So the peak reverse voltage that appears across the thyristor would be how much? It would be equal to minus Vm. Okay, as you can see from here. Okay, so the peak reverse voltage that appears across the thyristor anode and cathode if I didn't properly, cathode, anode and cathode terminals actually. So terminals is how much? Is Vm, as can be seen from this figure here. Okay. So what are the other things that can be observed from here? So if we have seen here that the delay angle alpha, okay, as you can see what we have, the alpha, no? So please remember that this delay angle alpha is measured from the beginning of each positive half cycle. Let me write it down here. Yes, some space here. So we can write the delay angle alpha. I said the delay angle alpha is measured from the beginning of each positive half cycle to the time instant when the gate trigger pulse is applied. Okay, so delay angle alpha is measured from the beginning of each positive cycle to the time instant when the gate trigger pulse is applied. Okay, so the thyristor conduction angle is from alpha to pi. Okay, so thyristor conduction angle is from alpha to pi. So if we are to write the conduction angle, so if you are to write the conduction angle of the thyristor, which is denoted by the symbol delta. Okay, so conduction angle will be equal to pi minus alpha. Okay, because the thyristor conduction angle is from alpha to pi, so the conduction angle, that is delta, can be written as pi minus alpha. Okay, so what we can easily write is that the maximum conduction angle is how much? It is up to pi. Okay, so one thing is clear, that the maximum, okay, maximum conduction angle, okay, is pi radians when the delay angle, alpha equal to 0. Okay, the maximum conduction angle is pi radians when the delay angle alpha is equal to 0. Okay, so and one thing is clear, that from this waveform, one thing is clear, that since voltage and the current, that is the output voltage and current, are in the same polarity, as you can see here, that the output voltage and current are in the same polarity, hence this rectifier can be faithfully taken to be a first quadrant operation. Okay, so it is a first quadrant operation. Why? Because both the voltage and current are in the same polarity. Okay, I think I need not have written this one because it is understandable from the figure. Okay, since both the voltage and the current are in the same polarity. Okay, now what we're doing, obviously we have to find out the performance parameters. Now what I can do, I can just give you the alpha value, and depending upon the alpha value, then you have to find out the performance parameters. Okay, so suppose the fire, I can say that the firing has occurred at alpha equal to suppose 30 degrees, 60 degree, like that, and we can then find out the our performance parameters. So what are the performance parameters we have to find out? If you recollect that in our last class, that in our class of uncontrolled rectifiers also, we found out the performance parameters. So obviously first one, which will be our average DC voltage. So as you can see, we'll be finding out the average DC voltage for this rectifier, which is equal to V0 DC equal to Vm by 2 pi 1 plus cos alpha. Okay, you may just check it. Okay, where Vm is equal to root over 2 into Vs, where Vs equal to the RMS value of the input AC supply voltage across the transformer. Then what we have, so the maximum average DC output voltage is obtained when alpha equal to 0, correct? When alpha equal to 0, we have the maximum average DC output voltage, and the maximum DC output voltage is VDM equal to how much? VDM would be equal to Vm by pi. Okay, understood? So the average DC output voltage can be varied by varying the trigger angle alpha from 0 to maximum of 180 degrees. Okay, so what we can do is that we can actually draw a graph where we can show that the DC output voltage is varying when we are changing the trigger angle alpha. That is also again understandable from the equation given. Okay, and what about the normalized output voltage? So normalized output voltage, as you can see, it is written as V0 DC by the VDC max, which is equal to VDC by VD by Vm by pi. So the solution of that gives us 1 by 2 into 1 plus cos alpha. So from this, we can easily again find out that how the output voltage actually changes with respect to our alpha. Okay, so then what we have to find out? We have to find out the RMS output voltage. Okay, so the RMS output voltage will be given by which equation? So obviously V0 RMS would be equal to root over of 1 by 2 pi integral of 0 to 2 pi V0 square d omega t, correct? So that is what we have here. So I have not written here half. You can understand that it would be root over. Okay, so obviously then V0 RMS, what you can write? So it would be 1 by 2 pi in terms of, since V0 is what? So V0 is equal to Vm sin omega t. So that is, so we are putting it here in this expression. And we are getting this. If you solve this, it will be yielding us this expression. You may please check these expressions. Okay, you may find it out yourself, because what will happen that if you try to mug up this type of equations, you will be getting confused. Okay, many of you will be getting confused. So try to deduce how the expressions are coming. Then it would be much easier, because these type of problems will be carrying at around 10 marks. So please remember this thing. Okay. So then what are the other performance parameters then? So obviously we have to find out the output DC power. So it would, the equation is given as P, so it is P0 equal to V0 DC into IDC, that is PDC equal to VDC into IDC, obviously where VDC is the average or DC value of the output voltage and IDC is the average or the DC value of the output load current. Then we have to find out our output AC power also. So as you can see, output AC power P0 AC equal to V0 RMS into I0 RMS. What about the rectification ratio? Eta is equal to P0 DC by P0 AC. What about the output voltage? Again, the output voltage can be considered to be composed of two components. See, we have done these things in the case of our uncontrolled rectifiers also. Okay, the same things will be, we are again finding it here. So the output voltage can be considered to be composed of two components. One is the DC component and another is the AC component or the ripple component. Okay, so one is the AC component. One is the DC component, that is our V0 DC, that's the DC or the average value of the output voltage, and another one is the ripple component, that is our V0, that is our VAC, that is RMS value of all the AC ripple components. So what is the total RMS value of the output voltage? V0 RMS will be equal to root over of V0 square plus VR square. So VAC would be equal to how much? We will be equal to VRMS, VRRMS, which is equal to V0 square RMS minus V0 square DC. Okay. What about the form factor? Form factor is equal to V0 RMS by V0 DC. What about the ripple factor? That is equal to how much? Means ripple factor will be equal to root over of form factor square minus 1. Okay. So please remember that I have not solved any particular problem, but you may try to solve this type of problems where the alpha value will be given from any book. Okay. What about the sixth one? Obviously, since we are using a transformer, so we have to find out the transformer utilization factor. So that is that UF, as you can see, it is P0 DC by Vs into Is, where Vs is the RMS value of the transformer secondary output voltage, and Is is the RMS value of the transformer secondary current. Okay, that is the RMS line of the supply current. Then we have to find out the displacement factor or the fundamental power factor, that is our cos phi. And then we have to find out the total harmonic distortion factor or the harmonic factor. So obviously it is a measure of the distortion in the output waveform and also referred to as the total harmonic distortion. Okay, so it would be harmonic factor equal to Is minus I square minus I square S1 by I square S1, where obviously IS1 is the RMS value of the fundamental component of the input supply current and I is the RMS value of the input supply current. Then what we have, the input power factor PF, that is equal to IS1 by Is into cos phi, and the crest factor equal to peak input supply current by RMS input supply current. I hope it is clear, because I am again repeating the same thing, that the alpha value would be given to you and you have to find these performance parameters if asked for a single phase half wave controlled rectifier. Okay, so what is the input current actually for a single phase half wave control rectifier? Let us see this one. So as you can see, this is the source voltage. So Vs is the supply voltage at the transformer secondary side, and Is is the input supply current at the transformer secondary winding current. See, this is the input current. Okay, so it is basically a square wave because there are many harmonics in the system. Okay, so Is1, as you can see here, the dotted one. So this is the fundamental component of the input supply current. Okay, and Is is the input supply current. This is the input supply current. Okay, and its fundamental component is this one. So fundamental component along with all the harmonics will be giving us this type of waveform, square waveform. Okay, so what is our IP? As you can see, IP is the peak value of the input supply current. Then what we have the phi, as you can see here. So phi is the phase angle difference between the fundamental component of the input supply current and the input supply voltage. Okay, so this phi, actually this line should be around somewhere here. You can understand that it should be around here. Okay, so this should be phi actually. So from where I have copied it, they have written in this way. So I can understand that the fundamental component of the input supply current and the voltage, the difference between this is the phase angle difference. This is the phase angle difference phi. Okay, and we have another phi that is known as our displacement angle. Now what will happen, that for a RL load, this displacement angle phi is given as how much? Equal to tan inverse omega L by R for an RL load. Okay, what is happening for RL load, we'll be seeing it in the next slide only. Up to here it is clear? Up to here it is clear? Yes?
Yes, sir.
Okay. So next what we have, we talked about a single phase half wave rectifier with a resistive load. Now let us talk about a single phase half wave rectifier with a RL load. Okay, so as you can see here, so this is the typical picture that I've taken for a single phase half wave phase control rectifier with RL load. So obviously what will happen here, one can understand that this thyristor T1 is forward biased during the positive half cycle of the input supply. When T1 is triggered, when T1 is on at omega T equal to alpha, suppose, okay, by applying a suitable gate trigger pulse to T1 during the positive half cycle, cycle of the input supply. Okay, so what will happen then? So the output voltage, this is the output voltage V0. So the output voltage across the load will follow the input supply voltage Vs when this T1 is on. Okay, and the load current will flow through this thyristor T1 and through the load in this downward direction as can be seen here. Okay, so the load current will be flowing through the thyristor T1 as can be seen here. That is our IT1. Okay, and through the load as can be seen here. Okay, and obviously what can one can consider that this load current that is flowing actually, okay, so this load current pulse flowing through T1 can be considered as the positive current pulse. Okay, it can be considered as a positive current pulse. Because why positive current pulse? Because that current will flow when or that current will flow during the positive half cycle of the input supply when the thyristor T1 is triggered at omega T equal to alpha. Okay, by applying a suitable gate trigger pulse to this gate lead of the thyristor T1. Okay, now what is happening, that please note that due to the presence of this inductor in the load current I0 flowing through T1 would not fall to 0 at omega T equal to pi. Okay, it would not fall to 0. What we saw then in the previous cases at omega T equal to pi, it was 0. But here at omega T equal to pi, the load current, okay, load current will not fall to 0. Okay, why? Because of the presence of the inductance in the load. Okay, so because of the presence of the inductance, the load current flowing, the load current I0 flowing through this thyristor T1 will not fall to 0 at omega T equal to pi when this input supply is starting to become negative. Okay, when the input supply is starting to become negative. Okay, so what can understand that because of the presence of this inductance, a phase shift will occur, a phase shift will appear between the load voltage and the load current waveforms. Okay, a phase shift will appear between the load voltage and the load current waveforms. Okay, here is the figure as you can see. Okay, here is the figure. Okay, so as you can see, when the supply voltage is going to 0, then also the current through the induct of this current is flowing through the thyristor because of the presence of the inductor, because the inductor is driving the current, because the inductive energy is driving the current through this thyristor T1. Okay, so as can be seen that the thyristor will be conducting from omega T equal to alpha to beta. Okay, the thyristor T1 will be conducting from omega T equal to alpha to beta. So the conduction angle of this thyristor T1 would be how much? So the conduction angle T1, the conduction angle of T1, that is delta, would be how much? It would be beta minus alpha. Okay, so this will be the conduction angle of our T1, which depends. So as you can see, this conduction angle depends upon the delay angle alpha and the load impedance angle phi. Okay, it will depend upon the delay angle alpha and the load impedance angle phi, because we have said that because of the presence of inductance, there would be a phase shift between the load voltage and the load current waveforms. Okay, so what you can say that basically this thyristor T1 will continue the load current until all the inductive energy stored in the inductor L is completely utilized, and the load current through this thyristor T1 will fall to 0 at omega t equal to what we saw from there. At omega t equal to beta, the load current falls to 0. Okay, at omega equal to beta, the load current falls to 0. So one thing is clear, that the thyristor T1 will continue to conduct the load current until all the inductive energy stored in the load inductor is completely utilized. Okay, so the inductor মধ্যে যা যা স্টোর এনার্জি থাকবে সেটা সম্পূর্ণভাবে ব্যবহার হয়ে যাবে, এবং তারপরেই the load current through this thyristor T1 will be falling to 0 at omega t equal to beta. Okay, so obviously then what is the beta? Beta is known as the extinction angle. Okay, beta is known as our extinction angle. Okay, and how this beta is measured? Obviously, again, this beta is measured from the point of beginning of the positive half cycle of the input supply to the point where the load current falls to 0. Okay, let me write it down. So beta is measured from the point of the beginning of the positive half cycle of input voltage, input supply লেখা উচিত, of input supply to the point where the load current is 0, or load current falls to 0. Okay, so this is beta. So basically what we are trying to say, that it is measured from this point when the positive half cycle of the input supply to the point where the load current falls to 0. Okay, from this point to here, that is the value of beta that we are actually measuring. Okay, then as you can see from this particular figure, so in the left hand side we have our Vs, on the right hand side we have our V0. Okay, so since the V0 is also conducting, so as you can see, this is the output voltage waveform for a single phase half wave control rectifier with RL load. So this is the negative output voltage that we should be getting for omega t equal to pi to omega t equal to beta radians, and obviously beta will be the extinction angle depending upon the load inductance value. And I1 that we have shown here, that obviously would be equal to IT, would be obviously be equal to the load current I0, that is equal to our IS. I1 is nothing but IT1 actually. So IT1 take লেখার জন্য I1 লিখেছি. Okay, the current through the thyristor. Okay, so I1 equal to the load current, and that is also equal to the our supply current at the transformer secondary side. Okay, so obviously now what we have to do, we have to find out the expression for the output load current, how the thyristor conducting, how we have done that. Let us see this one. Okay, so as you can see, to derive the expression for the output load current, okay, to derive the expression for the output load current, current when the thyristor conducts. So at this condition, the instantaneous value of the input voltage is taken as Vs equal to Vm sin omega t. Okay, then what we have assumed, again, we have assumed that the thyristor is triggered by applying the gating signal at omega t equal to alpha. So the load current will flow through the thyristor during omega t equal to alpha to beta. That can be found from the simple KVL equation of L di0 by dt plus Ri0 equal to Vm sin omega t. Okay, so if we solve this differential equation, it gives the general expression for the output load current, which is of the form I0 equal to Vm by Z sin omega t minus 5 plus A1. Okay, A1 is a constant, A1 into e to the power minus t by tau. What is tau? Tau is written here, as you can see below. Tau is nothing but L by R, that is the load circuit time constant, where Vm will be obviously equal to the maximum peak value of the supply voltage, of the input supply voltage, that is Vs into root over 2. Then Z is obviously the load impedance, root over of R square plus omega L whole square. Phi is the load impedance angle, which is tan inverse of omega L by R. Okay. So so since this is a JL expression for the output load current, so obviously we have to find the value of this constant A1. So how can we do that? We know that means this value of this constant can be determined from the initial condition. What is the initial condition? So the initial condition is that at omega t equal to alpha, at this condition at omega t equal to alpha, our I0 is equal to 0. Okay. So if you put that expression, means that value, that I0 equal to 0, that is the load current or the initial load current or the initial value of the load current at I0 equal to 0 at omega t equal to alpha. If we put this one, then we can find out the expression for our constant A1. As you can see, this is the expression that we are getting. There's e to the power R into R alpha by omega L into minus of Vm by Z sine of alpha minus pi. And if you substitute this expression into here, so what we are getting, I0 equal to Vm by Z sine of omega t minus pi minus sine alpha minus pi into e to the power minus R by omega L into omega t minus alpha, where alpha is less than equal to omega t less than equal to beta. Okay, this expression can be found out. So then we have to find out the extinction angle. How can we find out the extinction angle? So this, as you can see, the extinction angle beta is the value of omega t at which the load current falls to 0 and the thyristor is turned off, can be estimated by using the condition that at I0 equal to 0, omega t equal to beta. So we can just put I0 equal to 0 in this expression, and in place of omega t, we'll be writing beta. So that's what we have done here. And we will be arriving at what equation? We are arriving at this expression. As you can see, we are arriving at the expression sine beta minus pi equal to sine of alpha minus pi e to the power minus R into beta minus alpha by omega L. Okay, so the extinction angle beta can easily be determined from this transcendental equation by using the trial and error method. Okay, so after beta is calculated, we can easily determine the thyristor conduction angle, that is delta equal to beta minus alpha. Please remember, in our since obviously we can understand that giving a transcendental equation and if you have to solve it by the iterative method, it will take huge amount of time. Okay, so that's why what we do generally is that we try to solve it. We try to means in our semesters we'll be giving the values. We'll be giving the value of beta, and you may be asked to find the other part. That is, you may be asked to find the value of alpha. Like that, we can give any problem. Okay. So as you can see from this expression, that the conduction angle delta, that is from the expression delta equal to beta minus alpha, the conduction angle delta increases as the alpha value is decreased for a specific value of beta. So conduction angle for a purely resistive load or for an RL load, when the load inductance is negligible, the extinction angle beta will be equal to pi, and the conduction angle will be pi minus alpha. So what we can find out, the average DC load voltage then. So as you can see, the average DC load voltage would be 1 by 2 pi integral of alpha to beta. Okay, integral of alpha to beta V0 d into omega t, where V0 equal to Vm sin omega t for omega t equal to alpha to beta. If we solve this is the expression that we are getting, that is Vm by 2 pi into cos alpha minus cos beta. So during the conduction period, the instantaneous output voltage, as you can see, is negative. So what we can understand, that this reduces the average DC output voltage when compared to a purely resistive load. So if you are to compare the average DC output voltage of a single phase half wave phase counter rectifier of an RL load with a purely resistive load, we can understand that because of the conduction period, the instantaneous output voltage in case of our single phase half wave phase counter rectifier with RL load is less compared to the average DC output voltage of a purely resistive load. Okay, because the instantaneous output voltage is negative because of the conduction from omega t equal to pi to omega t equal to beta. And obviously again we can find out the average load current, that is equal to VDC by RL. So Vm by that, if you put the expression, that would be Vm by 2 pi RL into cos alpha minus cos beta. Okay. Next, what we have next is suppose that we are using a freewheeling diode. Okay, suppose we are using a freewheeling diode to this to this single phase half wave controlled rectifier. So let us see the waveforms. As you can see, so what is happening? So this is FWD is nothing but the freewheeling diode. So as you can see that during this freewheeling time, the load is shorted. This load is shorted by the conducting freewheeling diode, and the load voltage is almost zero. Okay, so as you can see here, when supply voltage was starting to getting to negative, the load voltage is shorted by this freewheeling diode, and that's why the load voltage is almost zero. Okay, so okay, uh, means we can understand that we are assuming that it is almost zero, but it may not be exactly zero if the forward voltage drop across the freewheeling diode is also considered. Okay. Uh, so if it is neglected, then we can say if the forward voltage drop across the conducting freewheeling diode is neglected, then we can say that the load voltage is almost zero. Okay. And because of it, what will happen? One can understand that since uh, there is no negative region in the load voltage, one can understand that with the presence of this freewheeling diode, the average output voltage will be improving for a single phase half wave control rectifier with RL load and freewheeling diode. Okay, so the average output voltage would be improving, but at the same time, you can see that the average output voltage of a single phase half wave control rectifier with RL load and freewheeling diode is the same as that of a purely resistive load. Okay, because in the purely resistive load also we are getting this waveform only. Okay, and as you can see that the output voltage across the load appears similar to the output voltage of a purely resistive load. Okay, resistive load এর ক্ষেত্রে যে output voltage পাচ্ছি এই RL load with freewheeling diode এর ক্ষেত্রেও কিন্তু আমরা একই load voltage আমরা পাবো. Okay, so what we can say that এখানে লিখে দিচ্ছি that average output voltage is same as that of a purely resistive load. Okay, average output voltage is same as that of a purely resistive load, as you can see here. Okay, average output voltage is same as that of a purely resistive load. তার জন্য for a rectifier, single phase half wave control rectifier with RL load and freewheeling diode. Why? Because of the presence of the freewheeling diode, what is happening? আমি আবার লিখে দিচ্ছি load voltage, or you can say the load is shorted. Load is shorted by the conducting freewheeling diode, and the load voltage is almost zero if we are neglecting the forward voltage drop across the conducting freewheeling diode. Okay, so what we can say, so this improves the average load voltage. Okay, average output, average output load voltage. Okay, so what can happen? One thing, as you can see here, that what about the load current? So load current would be, it is continuing from omega t equal to pi, it is continuing up to omega t equal to beta, as was in the previous case. Load current কিন্তু কোনো চেঞ্জ হচ্ছে না, কিন্তু আমার আউটপুট ভোল্টেজে কিন্তু ইমপ্রুভমেন্ট হয়ে গেছে. দিস ইজ দ্য লিড কারেন্ট ওয়েভফর্ম. লোড কারেন্টে কিন্তু কোনো চেঞ্জ হচ্ছে না, কিন্তু আউটপুট ওয়েভফর্মে যে এই পোর্শনটা, এই নেগেটিভ পোর্শনটা কিন্তু আর থাকছে না. ওকে, যার ফলে অ্যাভারেজ আউটপুট ভোল্টেজটা কিন্তু ইমপ্রুভ হচ্ছে. So what we can say that if the inductance value is not very large, then the energy stored in the inductance is able to maintain the load current only up to omega t equal to beta. Okay, as you can see here. Okay, where this beta, I think it is written here. Here. If the inductance value is, let me just make it large. Here. Okay. So as you can see that if the inductance value is not very large, the energy stored in the inductance is able to maintain the load current only up to omega t equal to beta, where pi less than beta less than 2 pi, well before the net gets pulse and the load current tends to become discontinuous. আমরা আগে বলেছিলাম যে যখনই কারেন্টটা আমার জিরো হয়ে আছে তখন কি বলছি, সার্কিটটা আমরা ডিসকন্টিনিউয়াস বলছি। সাপোজ লোড কারেন্ট যদি খুব বেশি থাকতো, ওকে, সো দ্য লোড কারেন্ট যদি খুব বেশি, মানে লোড কারেন্ট সরি, লোড ইন্ডাক্টেন্স ভ্যালুটা যদি খুব বেশি থাকতো, তাহলে আমরা কি করতে পারতাম, তাহলে লোড কারেন্টটা আমরা অনেকটা সাস্টেন করতে পারতাম ফর দ্য নেক্সট ট্রিগার পালস। তাই যদি হতো তাহলে কিন্তু কারেন্টটা কখনো আমার জিরোতে আসতো না। তাহলে তখন কি বলতে পারতাম, যখন বলতে পারতাম যার দ্বারা লোড কারেন্ট will be in a continuous conduction state, correct? But here as you can see that since the load conductance is such that it is able to maintain the load current only up to omega t equal to beta, so that is well before the net gate pulse. Therefore, the load current tends to be discontinuous because it is tending to be zero. Okay. So during the conduction period of alpha to pi, let me see here. Yes. So during the conduction period of alpha to pi, the load current is carried by the thyristor, and during the freewheeling period from pi to beta, okay, during the freewheeling period, this is the freewheeling period from pi to beta. Okay, so during the freewheeling period from pi to beta, the load current is carried by the freewheeling diode. Okay, so the value of this beta depends on the value of, as you can see here, the value of beta depends on the value of the resistance and the load inductance and the forward resistance of the freewheeling diode. Generally what we have, the value of beta will be lying between pi and 2 pi. Okay. Next in what we had, so this is the waveform of the load current. As you can see, waveform of the load current in single phase half wave control rectifier with a large inductance and freewheeling diode. As you can see, since we are using a large inductance, the load current will become continuous. Okay, so load current becomes continuous and the load current does not fall to zero for large value of the load inductance, and the ripple in the load current, as you can see, also decreases. Okay, because here the load current will be zero, তাহলে দেখো রিপেল কন্টেন্টটা কত বেশি, whereas in this case when if we are considering a very large inductance value, so the load current will be the ripple in the load current waveform would be less compared to the previous case where the load inductance was very less. Okay, so এত কিছু বললাম, but there are certain disadvantages of using this single phase half wave control rectifier. So let us see what are the disadvantages. So the disadvantage is that it gives us low output DC voltage, it gives us low output power and lower efficiency. There is a higher ripple voltage and ripple current. Okay, though because of the large inductance, this is the load current waveform, but again see there's a high ripple content. Okay, there's a high ripple content in the load voltage as well as the load current. Okay, so high ripple content in the voltage and the ripple current. There will be low transformer utilization factor, and the input supply current waveform has a DC component which can result in DC saturation of the transformer core, and that's why we as was in the previous case for an uncontrolled single phase half wave rectifier, here also for a controlled single phase half wave rectifier, these rectifiers are rarely used in practice. Okay, and how can we overcome these disadvantages? These disadvantages can be overcome by a full wave control rectifier circuit. Okay, so most of the practical circuits all use this full wave controlled rectifier circuits. Okay, and what is the gating sequence of this single phase half wave control rectifier? The gating sequence is nothing but we'll be generating a pulse signal at the positive zero crossing of the supply voltage Vs. Okay, as can be seen from the figure here, this is the gating pulse. Okay, so we'll be generating a pulse signal at the positive zero crossing of the supply voltage, and we can delay the pulse by the desired angle alpha and apply it between the gate and the cathode terminals of the thyristor T1 through a gate isolating circuit. Okay, I think that is written also here. Okay, so we'll delay the pulse by the desired angle alpha and apply it between the gate and the cathode terminals of thyristor T1 to a gate isolating circuit. Okay, if time permits, in the after we have finished the control rectifiers, I may talk about the gating circuits. Okay, but for the timing, we'll not be talking about it. Let us see if we can, if we are able to finish the syllabus for the control rectifiers, then only we will talking about this gating signals. I hope it is clear till now. Yes.
Yes, sir.
Okay.
Yes,
So
sir.
thank you everybody. We am stopping the recording and stopping the presentation also. Please note that on next Wednesday, yes, next Wednesday, I might be able to take the class. I may not. Okay. So if no mail is received by Tuesday, please remember, if no mail is received by Tuesday night, then you can assume that there will be no class on Wednesday. Okay. But if you have received any mail, so obviously I will be telling it through mail. Okay. So if I have not mailed you, please remember that no class will be happening on next Wednesday. Okay, please understand this. Okay, so please do not bother and just